This is a little bit of a not a rant, but it's like why is Shor's algorithm so complicated to explain and so confusing? It's like, I don't know, it just feels like people want to make it complicated to explain things, and I get it. I really get it. That you want to use the maths because you want to, it's necessary in research to prove that it's correct and blah 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 blah. But it's like if we really want to help people learn stuff, if we really want to bring that to engineering and to sort of the kind of uh, the kind of simple-minded engineering. It's like, it's not that I'm calling myself simple-minded, but I mean, there's a certain degree of practicality that we need to bring to this whole quantum computing thing if we want people to be sort of creative and then actually work on some breakthroughs. And you probably need, of course, you need the formalities and all this kind of stuff, but really, it shouldn't be that complicated. It's like you can probably explain phase estimation in like 5 minutes at intuition level. I mean, I know I tried in the past video and I didn't really make it even in 20 minutes, I think. But I was kind of thinking, why is it so complicated? Really, because really one of the things that the quantum computing book from O'Reilly does really well is this concept of introducing the basics, then talking about sort of primitives, like quantum primitives. And quantum primitives are like higher level blocks of conceptual logic that you can use to compose other big things. And one of them is the quantum Fourier transform, another one is phase estimation, another one is like amplitude amplification that is used in Grover's search algorithm. And it's like, this is fairly, the reason phase estimation is complicated to explain is really, in my opinion, is this part here. And I think that's what's causing the confusion, because I haven't really found anywhere right now where this is explained in a way that it kind of makes sense. So even the so the even the Kindle, like the O'Reilly people kind of, I think they do a better job than most of the stuff out there, but it's still phase estimation. But it feels still, it's not, maybe even, it's not like it's not the best they can do. Quantum phase estimation. Exactly. This is where I wanted to go. So they explain quantum phase estimation with the concept of eigenphases, and I think that's an interesting thing, because it explains that without the context of Shor's algorithm. So they talked about, okay, doing phase estimation on a Hadamard gate, and that helped me a lot to connect the dots. But I think the context of Shor's algorithm is important as well, and really, just the fact that it's extremely complicated to find out there a simple example that is not a weird fancy optimization of that to actually teach, right? I think people, what you find out there a lot is you found some papers on like fast thing that's called like modular controlled modular multiplication, or but you just find like super optimized circuits for that, and they don't really help you understand the principles of the whole thing here, which are, in my opinion, fairly simple at the intuition level, right? Literally, you prepare superposition, right? You basically program, you program your function that you're trying to get the phase of in a way that that is controlled by the superposition. Because what you want to do here is you want to have that phase kickback effect that basically encodes, maybe not the direct answer, but it encodes the different results in the superposition, so that you, at this point in time here, get sort of your your superposition with different phases. I don't know how to draw that, like phase like that, phase like that, phase like that, phase like that, phase like that. So you get that thing circular, which you then feed into the quantum Fourier transform, and out of that you actually read out you know, what's the frequency of that. And sure, Shor's algorithm takes more than that. If you want to understand the whole thing that happens out of the quantum computer, it requires math. I mean, because it's basically a mathematical trick, right? So it's like a way to see the prime, a way to find the prime numbers, exploiting the fact that you can do this with that function, and then in the fact that that function is sort of repetitive, right? And that's all that's in it. I really wanted. I said in the other video I wanted to kind of give an example, but it's just I haven't been able to find anything there that it's sort of straightforward enough to put into an actual circuit, because the problem is to even to factor 15, right, which is like 5 times 3, it requires a relatively big amount of qubits, which make the current tooling complicated to use. Not even talking about simulators, not even talking about actual NISQ computers. So, and yeah, that's really it. It's there's no other secret in here. I don't know why there's no one just explain. Like, there's a lot of videos and there's a lot of articles, there's a lot of stuff out there that try to explain things in and out with the maths and why does this work. And I mean, even the IBM guys, I'm sorry people, but like if you go to the documentation and support, and then you go to the circuits, to the algorithms, right, and then you've got phase estimation. What am I? Grover's phase estimation. It's like you basically go through that, and then there's a point where it's like, yeah, and by the way, if this is just the same as applying the quantum Fourier transform, which is okay, but it doesn't. I mean, it didn't strike to me as obvious until I kind of realized that this is a phase kickback. And I'm sorry, because I think I haven't really done any video on the phase kickback, and I probably should do one, because it's an important effect. It's an important tool. It's a sort of a quantum thing. I like to treat it as a black box, in the sense that I think it doesn't make sense to try to explain why this happens at the intuition level. It's just, I assume it's a given, right? So when you have a controlled operation, when you have sort of a 2-qubit or multi-qubit operation that touches the phase of one qubit, that affects the other one as well. And I think a lot of people get super confused, because it's like, how is it possible that if I'm doing something here, then I can actually read an answer here when there's no, these things seem to be independent? It's because we tend to explain things in a weird way and say that's the control bit for this one, the control qubit for this one. But we don't realize that because of that relationship, that kind of correlation, maybe not correlation, but kind of entanglement, or I don't know, it's maybe not entanglement, but it's like, there's this kickback, and that's definitely a useful trick. So I'll leave it here, really. I didn't want to. Maybe down the road I'll work on an example if I have the time, but I feel I'm happy enough with this, and I'll really move on. Because there's plenty of other stuff that I wanna cover in the channel, and it feels like really going down to build an example would probably take too much of my time, actually, which is not much. But really, it's as simple as that. It's as simple as that. I'll really repeat it again. Just you're just making some calculations in here, some arithmetic, right? That it leaves a trace. So basically, of course, you have to implement it in a certain way, and that's the tricky part. And it's complicated to figure out how to implement that, and how to design that. So and that kicks back into the superposition. So your superposition kind of ends up with a phase encoded wave. And this is exactly what the quantum Fourier transform wants or needs as an input to then give you the frequency or the set of frequencies as an outcome. And that's what you want, because with that phase, then you can go to the classical part of the algorithm, and then do the math, and then check whether that's a good answer or not. So, and if not, you kind of repeat the whole thing again with another number that you pick up randomly. So that's it, really. There's no magic to it. And to some extent, there's some magic, but it's not like, I don't know. I feel good and bad at the same time. I always thought that was an extremely fancy thing. I think, and sure, it is complicated, but intuitively, it's not. It's really simple. It's a really simple concept intuitively. Um, cool. I hope that is helpful. And I mean, if I'm saying something that's totally wrong, just let me know. But I feel quite comfortable with that understanding of Shor's algorithm, and this is really going to be the last video that I make about it. I might come back to this later on. I don't know. See how things evolve. Perfect.